Your presenter today is Tara Blank. Tara has a doctorate in biology and has studied diverse environmental issues such as toxicity in water supplies, hypoxia's effects on fish, and conservation efforts to save the Cibolo Creek in Texas. She works closely with architects, designers, engineers, scientists, and other design professionals. Tara also works closely with building product manufacturers to develop health product declarations, also known as HPDs. We will now begin our presentation.
The learning objectives for this course include the following. Participants should be able to explain how to achieve the rainwater management credit using the percentile approach in O&M and option 1 in BD&C. Describe green infrastructure and low-impact development rainwater management strategies. Define percentile rainfall event. And review strategies to evaluate performance of rainwater management practices using freely available online tools. The rainwater management credit applies to the following lead adaptations in BD&C: new construction, core and shell, schools, retail, data centers, warehouses, hospitality, and healthcare. As you can see, the rainwater management credit can contribute 1 to 3 points depending on the lead rating system adaptation. Rainwater management is a new credit in LEED version 4. However, it has its roots in LEED v3. The stormwater quality and quantity management credits from LEED v3 have been combined into a single rainwater management credit for LEED v4. Additionally, the rainwater management credit applies to the following LEED adaptations in O&M: existing buildings, schools, retail, data centers, hospitality, and warehouses and distribution centers. In LEED O&M v4, the rainwater management credit can contribute 2 to 3 points depending on the LEED rating system adaptation. The intent of the rainwater management credit, shared verbatim between BD&C and O&M, is to reduce runoff volume and improve water quality by replicating the natural hydrology and water balance of the site based on historical conditions and undeveloped ecosystems in the region. Under Section 438 of the Energy Independence and Security Act of 2007, which is the reference standard for the rainwater management credit, federal agencies are required to reduce stormwater runoff from federal development and redevelopment projects to protect water resources. Federal agencies can comply using a variety of stormwater management practices, often referred to as green infrastructure or low-impact development practices. Green infrastructure and low-impact development rainwater management strategies and approaches improve upon that conventional approach by mimicking a site's natural hydrology. Rainwater is treated as a resource rather than a waste product. The methods and techniques in the rainwater management credit involve minimizing disturbed areas on the project site, limiting the amount of impervious cover on a site, and then infiltrating, filtering, storing, evaporating, or detaining rainwater runoff at or close to its source. Now let's explore some of the strategies being utilized by the City of Portland, Oregon. Portland has long been recognized by the EPA as having a robust and effective stormwater management program. Tim Kurtz, part of the Sustainable Stormwater Management Program, City of Portland, Bureau of Environmental Services, will now offer some insight into management practices.
It's very important for design teams to manage rainwater in the urban and suburban environment, as we've gotten rid of our forests and fields and creeks and streams and replaced them with roofs and parking lots and streets. just created a totally different runoff dynamic. The hydrology, how the water moves through the environment and atmosphere has totally changed. So we have a lot more runoff than we used to that we have to deal with. It's coming in a lot faster than it used to as well. And it's carrying pollutants now that we're picking up in the urban environment. And so these things can all cause damage, flooding, they can cause erosion, damage, of course, to sensitive habitat for species, and threat to the human species as well in a form of public health. Conventional rainwater design strategies typically involve getting the water off the surface as quickly as possible, getting it out of the way and putting it underground. And that works well as far as getting it off the surface, but now it's underground and we still have to deal with it. We still have a lot of runoff volume, it's still moving quickly, and it still has those pollutants in it as well. So now we have to move that water somewhere as well. So we have to build a very large and sometimes complicated drainage system underground in order to convey it where we need it to go. Also, quite often when we build a system, it can do one thing. So for instance, if we want to slow the water down, we could build a storage tank underground and put a small opening, an orifice in it to help slow how fast the water can move through the system. But we still have the same amount of water that we had before, and we still have to manage that. And it's still carrying all the pollutants that might have been there before, which can still be a problem. So then we have to start thinking, well, how can we address those other problems that we have? So we end up building multiple systems, and that can cost a significant amount of money.
According to the U.S. Environmental Protection Agency, stormwater runoff in urban areas is one of the leading sources of water pollution in the United States. Traditional urban areas typically include large areas of impervious surfaces such as roads, sidewalks, and buildings. These impervious surfaces prevent rainwater from infiltrating into the ground, and as a result, stormwater runs off these urban areas at higher rates and volumes. These higher stormwater rates and volumes can cause increased flooding and erosion and more pollution to surface waters, among various other impacts. Now, in a natural, undisturbed environment, rain that falls is quickly absorbed by trees, other vegetation, and the ground. Most rainfall that is not intercepted by leaves infiltrates into the ground or is returned to the atmosphere by the process of evapotranspiration. Very little rainfall becomes stormwater runoff in permeable soils, and runoff generally only occurs with larger precipitation events. Again, traditional development practices cover large areas of the ground with impervious surfaces like roads, parking lots, and buildings. Under developed conditions, runoff occurs even during small precipitation events, when that precipitation would normally be absorbed by the soil and vegetation. The collective force of the increased runoff scours stream beds, erodes stream banks, and causes large quantities of sediment and other entrained pollutants to enter the water body each time it rains. Again, the intent of the rainwater management credit is to replicate the pre-development hydrology to protect and preserve both the water resources on site and those downstream. For example, if prior to development 25% of the annual rainfall runs directly into a stream and the remainder infiltrates into the ground, then the post-development goal should be to limit runoff to 25% of the annual precipitation while maintaining the correct aquifer recharge rate. This has the benefit, in most cases, of delivering water to the stream at approximately the same rate, volume, duration, and temperature as the stream had naturally evolved to receive prior to development. The result will be to eliminate or at least minimize the erosion of stream beds and stream banks, significantly reduce the delivery of many pollutants to water bodies, and to retain historical in-stream temperatures. Designing facilities based on the goal of maintaining or restoring pre-development hydrology provides a site-specific basis and an objective methodology with which to determine appropriate practices to protect the receiving environment. Using pre-development hydrology as the guiding control principle also allows the designer to consider climatic and geologic variability and tailor the solutions to the project location. Thus, the need for a one-size-fits-all approach is rendered unnecessary since the design objective is dictated by the pre-development site conditions and other technicalities of the project site and facility. So instead of prescribed approaches dictating discharge volumes or flow rates, site assessments of historical infiltration and runoff rates will inform the designer and provide the basis for a suitable design. There are many beneficial outcomes when implementing green infrastructure and low-impact development rainwater management strategies. One benefit that we should expect to see is cleaner water. The use of plants, soils, and water harvesting and use practices can reduce stormwater runoff volumes and pollutant loadings and the frequency and magnitude of combined sewer overflows. Another expected benefit is adequate water supplies. Using soil-based vegetated infiltration systems can be used to recharge groundwater and maintain stream base flow. By recharging groundwater aquifers, aquatic ecosystem health is maintained and base flows are increased, which helps ensure more constant flows for drinking water withdrawals. Harvesting and reusing rainwater also reduces the need to use potable water for all uses and can reduce both the infrastructure and energy needed to treat and transport both drinking water and stormwater. And finally, we should expect source water protection. Low-impact development rainwater management strategies provide pollutant removal benefits, thereby providing some protection for both groundwater and surface water sources of drinking water. In addition, the approach provides groundwater recharge benefits. And according to the EPA, there are even more benefits to using these strategies, like cleaner air. Trees and vegetation improve air quality by filtering many airborne pollutants and can help reduce the prevalence of respiratory illnesses. We can also expect to experience reduced urban temperatures. Summer city temperatures can average 10 degrees higher than nearby suburban temperatures. High temperatures are also linked to higher ground level ozone concentration. Vegetation creates shade, reduces the amount of heat absorbing materials, and emits water vapor, all of which cool hot air. Reductions in impervious surface and the use of light-colored pervious surfaces can also mitigate urban temperatures. Using these types of strategies can also help to mitigate the impacts of climate change. Now, while climate change impacts and effects vary regionally, low-impact development rainwater management strategies can provide adaptation benefits for a wide array of circumstances. They can be used to conserve, harvest, and use water, to recharge groundwaters, and to reduce surface water discharges that could contribute to flooding. There are also mitigation benefits such as reduced energy demand and carbon sequestration by vegetation. Another benefit cited by the EPA is increased energy efficiency. Green space helps lower ambient temperatures and, when incorporated on and around buildings, helps shade and insulate buildings from wide temperature swings, decreasing the energy needed for heating and cooling. Diverting stormwater from wastewater collection, conveyance, and treatment systems can reduce the amount of energy needed to pump and treat the water. energy efficiency not only reduce costs, but also reduce generation of greenhouse gases. There are also benefits to the community. Trees and plants improve urban aesthetics and community livability by providing recreational and wildlife areas. Studies show that property values are higher when trees and other vegetation are present. Increased green space also has public health benefits and has been shown to reduce crime and the associated stresses of urban living.
Some of the most significant challenges to managing rainwater are space. We need to find space in order to do it. Quite often with our developments, we're doing lot line to lot line development. There's not a lot of space. Even when there is, it's at a premium. We need to maintain the uses that the owner of the building wants for their site, including parking, freight movements, a number of different things. And even in the public right-of-way, we have bike lanes, we have car movement, other things that are competing for space as well. So finding the right space to make it work is always a challenge. We also have things like utilities underground. We're often doing retrofitting where we're working in environments that have already been developed, and so we have to work around the other infrastructure that's already in place. So things like water lines, gas lines, power, communications are all sitting there underground and make it a challenge sometimes to fit things in. We also have to look at other site conditions, slopes, how close we might be to a building. Contamination under the ground, if we're working in an industrial area, for instance, are all factors that we have to consider when we're working with green infrastructure facilities. I think in thinking over just in general what's most beneficial in designing for stormwater management, having a multidisciplinary team right from the beginning as early as possible is really crucial. It's always been traditional, really, for one group to work on a project in isolation, come up with an idea, and then not really understand the consequences, perhaps, to the others that are working on things. So having engineers, architects, landscape architects all working together from the beginning provides an opportunity not only to have a great design, but to also make sure that all the problems that you might encounter are considered before you actually get to construction, which is incredibly valuable. Innovation is really something that I hope that people wouldn't be too afraid of. Even if it's not something that's been tried before, if it's something that would work really well on a site and you want to try something different, being open to that and trying to do that. It may not be easy to do it, but it may open the doors for something that would be very beneficial for everyone, not just that particular project. And then I'd also say too, especially from a public agency who's worried about the long-term costs of these facilities as well, maintenance is a huge one. So designing something that's also going to be something that will be easy to maintain going forward is extremely important.
Now we'll discuss the requirements for the rainwater management credit using a percentile of storms calculation. Option 1 under BD&C, or the only option for O&M. Select the appropriate option and path, if applicable, for the project. First, investigate data sources for natural land cover conditions and choose option 1 for BD&C projects if information is not available. Option 1 is for BD&C project teams that, after research, cannot adequately determine the natural land cover conditions of the site. So, what is a percentile rainfall event? A percentile rainfall event represents a precipitation amount that the chosen percent of all rainfall events for the period of record do not exceed. For example, the 95th percentile of rainfall events is the measured precipitation depth accumulated over 24 hours that ranks as the 95th percent rainfall depth based on the range of all daily event occurrences during the period of record. The 24-hour period is typically defined as 12 o'clock a.m. to 11:59 p.m. Option 1, percentile of rainfall events, path 1, 95th percentile. This path awards 2 points, except for healthcare projects, which only awards 1 point. In a manner best replicating natural site hydrology processes, manage on-site the runoff from the developed site for the 95th percentile of regional or local rainfall events using low-impact development and green infrastructure. Use daily rainfall data and the methodology in the EPA's technical guidance on implementing the stormwater runoff requirements for federal projects under Section 438 of the Energy Independence and Security Act in order to determine the 95th percentile amount. The first step a design team needs to take is to obtain rainfall data for project location. Collect at least 10 years of historical rainfall data, or as much historical data as possible from all seasons to account for seasonal variability. If the team submits less than 10 years worth of information, explain why additional historical data are not available. For projects in the U.S., long-term rainfall data for many locations are available through the National Climatic Data Center. Use this database or another source to identify the reference location closest to the project site where similar precipitation patterns are expected. The National Climatic Data Center website is part of the National Oceanic and Atmospheric Administration. It maintains the world's largest climate data archive and provides climatological services and data to every sector of the United States economy and to users worldwide. Records in the archive range from paleoclimatology data to centuries-old journals to data less than an hour old. The center's mission is to preserve these data and make them available to the public, to business, industry, government, and researchers. For project locations outside of the United States or other locations not covered by the National Climatic Data Center, obtain information from local airports, universities, water treatment plants, or other facilities that maintain long-term precipitation records. If rainfall data for the project location are not available through the National Climatic Data Center database, other databases that may be useful include the UN Food and Agriculture Organization and Aquastat. Data must include the location of the monitoring station, the recording time, usually the start of a time step, and the total precipitation depth during the time step. Collect daily historical rainfall data from a consistent source whenever possible. If data must be combined from multiple monitoring stations, interpolate or average rainfall data from 3 or more stations around the site to even out any discrepancies with the primary station. The next step is to determine the value for the 95th percentile rainfall events. Using the historical rainfall data collected, calculate the rainfall value for the 95th percentile in either inches or millimeters. This is the precipitation amount that 95% of all rainfall events for the period of record do not exceed. So let's use the following steps to determine the 95th percentile rainfall events. First, the design team needs to obtain a long-term daily precipitation data set for the project location. Again, for U.S. projects, this can be data from the National Climatic Data Center website. In general, a 30-year period of rainfall record is preferred for the analysis. But again, at least 10 years of data must be included if available. Next, import the data into the USGBC Rainfall Events Calculator or another spreadsheet. The USGBC Rainfall Event Calculator can be found at the USGBC website under the Resources section. There are several tabs here to enter information. The Historical tab is where you enter rainfall from the percentile storm event. The historical data also include the date, recording time, location, and total precipitation. The next tab is where you input the strategies information. This should include the runoff volume required to be managed on site. The low impact development and green infrastructure strategies need to be listed here, as well as the amount of volume managed per strategy. Finally, there is the tab for the summary. The summary should include what path you are seeking under option 1, as well as the total rainfall from the percentile storm event and total runoff volume managed on site. Use the Summary tab in the calculator to complete the form in Lead Online. If using another spreadsheet, organize daily precipitation records in a single column in any order. Review the records looking for anomalies and identify and remove any erroneous or flagged data points. Also remove rainfall events of less than 0.1 inches or 2.5 millimeters. The amount of precipitation from these small events generally produces no measurable runoff because of absorption by permeable surfaces and interception and evaporation by impermeable and vegetated surfaces. The USGBC calculator determines the 85th, 95th, and 98th percentile rainfall amounts. If using another spreadsheet software, apply a percentile function or similar to obtain results. The next major step for option 1 is to calculate runoff volume to be managed on site. The design team will need to calculate the total volume of runoff, either in cubic feet or cubic meters, which corresponds to the 95th percentile of rainfall events for that site in its post-developed condition. This is the amount that the project will need to manage entirely on site through green infrastructure and low-impact development techniques. Different methods can be used to calculate the runoff volume. Examples include the modified rational method, Natural Resources Conservation Service method, sometimes called the SCS method, as described in Technical Release 55, and also the US EPA Rainwater Management Model. Now we'll explore how the City of Portland determines runoff volume for city projects.
Yeah, so for the City of Portland, we determine runoff volume for our projects in a couple of different ways. One, under the Stormwater Management Manual for the city, we have some tools that use the Santa Barbara hydrograph method, so similar to the modified rational method that's out there. And it'll give you an idea what peak flows and the volumes will be coming off your site and how they'll be routed through. For some of our more complicated public works projects that we do, we'll actually do continuous simulations. So we use a software called XP Swim, and that's based on the EPA Stormwater Management model. And it adds a graphic user interface and some post-processing tools. And it allows us to play with different configurations of both gray and green infrastructure. So it allows us to place a green street at an intersection, for instance, and see what kind of impact that might have. And we can determine that's not enough and then go through and add some more until we finally get to the point where it's working correctly.
Now, the final step for option 1 is to design strategies to manage runoff on site. Incorporate green infrastructure and low-impact development strategies into the site design to manage on site 100% of the total volume of runoff calculated for the 95th percentile rainfall event and the project's developed conditions. Work with the project's civil engineer, landscape architect, hydrologist, or other qualified professionals to determine design strategies and perform management calculations. We'll review 4 popular on-site rainwater management design strategies. The strategies include bioretention, permeable pavements or pavers, cisterns, and green roofs.
The City of Portland uses a variety of green infrastructure techniques to manage stormwater. There's the usual suspects like swales, planters, basins, or what we call rain gardens, and eco-roofs as well. But also, we do a lot of tree planting, and trees aren't always first thought when we think of green infrastructure, but they're a huge component of green infrastructure in urban environments where we're usually lacking vegetation. They intercept stormwater and provide many other benefits as well. Also, just maintaining our natural riparian areas around our creeks and streams so that we can manage floods better, and they're much more resilient in the system as well. And restoring those that have degraded over time as well provide huge benefits.
Bioretention practices are popular because these systems generally have the lowest cost per unit of stormwater treated. In most cases, a combination of practices helps create an integrated treatment system. Bioretention utilizes soils and both woody and herbaceous plants to remove pollutants from stormwater runoff. Rain gardens are a widely used bioretention design strategy. Bioretention typically treats stormwater that has run over impervious surfaces at commercial, residential, and industrial areas. For example, bioretention is an ideal rainwater management strategy for median strips, parking lot islands, and swales. These areas can be designed or modified so that runoff is either diverted directly into the bioretention area or is conveyed into the bioretention area by a curb and gutter collection system. Bioretention is usually best used upland from inlets that receive sheet flow from graded areas and at areas that will be excavated. The site must be graded in a manner that minimizes erosive conditions as sheet flow is conveyed to the treatment area, maximizing treatment effectiveness. Construction of bioretention areas is best suited to sites where grading or excavation will occur in any case so that the bioretention area can be readily incorporated into the site plan without further environmental damage. Bioretention should be used in stabilized drainage areas to minimize sediment loading in the treatment area. Bioretention is not an appropriate strategy at locations where the water table is within 6 feet of the ground surface and where the surrounding soil stratum is unstable. In cold climates, the soil may freeze, preventing runoff from infiltrating into the planting soil. The strategy is also not recommended for areas with slopes greater than 20% or where mature tree removal would be required. Clogging may be a problem, particularly if the bioretention area receives runoff with high sediment loads. Mount Tabor Middle School in Portland, Oregon offers several good examples of bioretention strategies. In 2002, the City of Portland Bureau of Environmental Services began planning for a project to protect residents from sewer backups adjacent to the school. The combined sewer on Pine Street surcharged during extreme rain events, pushed rainoff mixed with sewage into some residents' basements. An alternative to replacing the sewer lines was to retrofit the school with stormwater infiltration facilities. The design team planned a number of stormwater solutions around the perimeter of the building. The project included a rain garden, a vegetated swale, 6 smaller infiltration planters, and 3 dry wells. The facilities together manage runoff from approximately 2 acres of roof, playground, parking lot, and street surface. The rain garden technically is a planter. It sits between 2 wings of the building and collects runoff from the adjacent roof and asphalt play areas. The rain garden is valued by the school for the shade that it provides classrooms. The parking lot was retrofitted with a 1,400 square foot swale and a 200 square foot planter. Together, the systems manage runoff from 15,000 square feet of asphalt. The swale has multiple check dams to retain runoff and promote infiltration. Both the swale and planter are designed in a very large storm event to overflow safely toward the entrance of the parking lot, the street, and curb extension. This project is an example of how a retrofit project incorporated improvements that went beyond the immediate goal of rainwater management. Permeable pavements or pavers are transportation surfaces constructed of asphalt, concrete, or permeable pavers that are designed to infiltrate runoff. Permeable paver systems typically consist of strong structural materials regularly interspersed, which are filled with pervious materials such as gravel or sod. Precast systems can also be made up of lattice grids, or designers can use modular unit pavers such as interlocking concrete blocks. In addition to these structures, porous concrete is a permeable option that allows for infiltration through the concrete structure itself. Generally, porous pavement is not recommended for high traffic areas or for loading bays. Cisterns are containers or vessels that are used to store runoff for future use. Cisterns can store rainwater in significantly larger volumes in manufactured tanks or underground storage areas. Rainwater collected in cisterns may also be used in non-potable water applications such as toilet flushing. Both cisterns and rain barrels can be implemented without the use of pumping devices by relying on gravity flow instead. Rain barrels and cisterns are low-cost water conservation devices that reduce runoff volume and, for very small storm events, delay and reduce the peak runoff flow rates. A green roof or vegetated roof is designed with lightweight soil and planted with vegetation. Frequently, green rooftop area is limited by structural capacity. In addition, other rooftop equipment may need to be accommodated in this space, including HVAC systems and air handlers. Vegetated roofs consist of an impermeable roof membrane overlaid with a lightweight planting mix with a high infiltration rate and vegetated with plants tolerant of heat, drought, and periodic inundations. In addition to reducing runoff volume and frequency and improving runoff water quality, a green roof can reduce the effects of atmospheric pollution, reduce energy costs, and create an attractive environment. Green roofs have reduced replacement and maintenance costs and longer life cycles compared to traditional roofs. Now let's hear a discussion on green roofs from Matt Berlin, Outreach and Communications Coordinator for the Sustainable Stormwater Management Division of the City of Portland Environmental Services.
Roofs have been being implemented in Portland for about 20 years, and they started as an experiment. A coworker at the City of Portland had been to Europe and was inspired to try a green roof on his own garage. And like with other green infrastructure tools, the City of Portland studied the performance of these on a small scale and found that they were very successful at reducing volume and reducing flow to address some of the capacity problems in our sewer system, in our storm system. So green roofs allowed us to treat an otherwise unused space on a rooftop and turn that into a resource for our systems. So one of the benefits that comes from investing in green infrastructure is taking a systems approach to how we're addressing the problems we're trying to solve and their solutions. What green infrastructure allows us to do is bring in tools and solutions that create a more resilient system. When you look at a conventional gray system, it's defined, and in that system there's a capacity and a limitation. For example, our gray pipe system has a volume capacity. When that capacity is exceeded, the solution in a conventional manner is to replace that pipe with a bigger pipe. Green infrastructure allows us to have some flexibility on how you solve those problems. And when we're looking at things like climate change, things like increased rainfall in our city, green infrastructure allows us to adjust how we control those problems. And we're able to have more opportunities to solve those problems in ways that provide additional multiple benefits for the community. In the early 2000s, the City of Portland had several projects that we were monitoring for performance for stormwater management, and we used that information to build a case to integrate green roofs into our local policy. We have a green building policy for City of Portland owned buildings, where those buildings are required to include a green roof when practical, when they have either new construction or a re-roof project. We also have a number of incentives that were integrated into our policies, particularly to help with density bonuses, where a number of green roofs in certain parts of our city that were going through development were implemented in order to increase the amount of density in that area.
So let's look at some examples of green roofs. Portland Community College, or PCC, worked with the Portland Bureau of Environmental Services to create an educational stormwater project at PCC's central campus, the Climb Center.
So we're on the eco roof of the Portland Community College Climb Center, which is in the central east side of downtown Portland. This is a green roof project that was partially funded through the City of Portland's Eco Roof Incentive Program. We've worked over 5 years to fund around 130 plus projects all over the city, and this is one of the examples in the downtown area that's in a heavily industrial area. The incentive was a pretty simple process. We paid $5 per square foot for an eligible project, and we worked with the property owner to find an installer of their choice and design a system of their liking and have it installed, and then we would track that and make sure that the project was done as prescribed, and check back in a year and see how it's performing. Looks like it's doing pretty well after a year. We just want to make sure that it's going to operate the way that we hope, that it's going to soak up that stormwater, and it's going to provide those other benefits. And then we want to provide that technical assistance to the property owner if there are any challenges or anything that they want to celebrate about the project down the road. Most industrial areas, like this one, struggle to find opportunities for green space like trees, green streets, and green roofs. And so we've been lucky to find candidates in the Central East Side, partners like PCC, that have been willing to go the extra mile when they replace their roofs and include a green roof. This one's a pretty cool example. It's a pretty simple design, mostly sedum plants. It was planted about a year ago, and so it's still a little fresh. But you can see how the plant material is going to be filling in over time, and this does a lot of good for an area that's as industrial as the Central East Side, not only for stormwater management, but for mitigating the heat island effect, air quality benefits, habitat. There's an aesthetic value, and even the building owner can recoup some of the investment because the roof will last longer.
Stormwater runoff from the Climb Center's 5,200 square foot roof cascades over a concrete and steel slab waterfall into a rain garden. Runoff from 3,000 square feet of the adjacent street enters the rain garden after flowing under a steel grate that crosses the sidewalk. Stormwater that enters the rain garden soaks into the ground. In a very large rainstorm, excess water flows back into a catch basin in the street. The kiosk in the plaza describes methods of sustainability managing stormwater runoff. The kiosk itself is covered with a vegetated roof system that absorbs rain and reduces stormwater runoff. Portland artist Linda Wysong created the 6-foot steel sculpture titled I River. This design was inspired by the so-called log dogs, which were 6-inch steel spikes historically used by the lumber industry to bind log rafts together. The Multnomah Building, also in Portland, Oregon, has a 12,000 square foot green roof that is accessible to the public. The green roof was chosen because of its environmental benefits, longevity, and cost effectiveness over the long term. The roof absorbs rainfall that falls directly on it. The overall stormwater management goal was to reduce the peak runoff and volume that would otherwise contribute to combined sewer overflow events in the adjacent Willamette River. The footprint of the vegetated portion of the green roof is approximately 11,900 square feet. The catchment is 15,420 square feet, including the planted area, stone terrace, and pavers along the perimeter. Overflow drains to internal downspouts, which are connected to the combined sewer system. There are several crucial landscaping components that help to make the project a success. The growth medium is a proprietary aggregate from a local company. The 6-inch soil is comprised of pumice, perlite, digested fiber, and reclaimed paper pulp. The medium has a higher proportion of mineral content than it does organic content. The composition meets the structural requirements of the roof and is free draining to promote plant growth. The project designers selected plants according to criteria that included adaptability to roof conditions, ecological function, local availability, drought tolerance, aesthetics, and maintenance requirements. Portland's extensive summer dry periods made an irrigation system a requirement. The permanent drip irrigation system is 3 inches below the soil of the surface and delivers water directly to the roots. Soil moisture sensors control the drip irrigation system. This project is a great example of how a green roof can be a central feature in an urban environment. Nearby offices can enjoy the views of the roof. The roof will provide ongoing benefits for the county and city in terms of rainwater management and reductions in heating and cooling costs for the building. The roof provides habitats for birds, butterflies, and other wildlife. In addition, the public is encouraged to plant edible gardens in a designated area of the roof, of which 100% of the produce goes directly to a local food bank. Design teams using rainwater management option 1 should use an empirical, statistical, or mathematical method to confirm that the total volume of rainwater managed by the product's green infrastructure and low-impact development measures will fully manage the total runoff volume through infiltration, evapotranspiration, or capture and reuse. Calculations must account for the site-specific soil characteristics, the soil infiltration rate, and the storage capacity of all measures implemented. For multi-tenant complex projects, the requirements may be met using a coordinated approach for multiple building projects. This could include a group of distributed low-impact development techniques within the boundary of the master plan to manage rainwater generated from the project site. If a coordinated approach is used for the multi-tenant or multiple building areas, distributed low-impact development techniques based on a watershed approach are required. Accordingly, highly centralized approaches such as large ponds or wetlands that manage all of the runoff from the master plan site do not meet the intent of this credit. Instead, design strategies to manage runoff as close as possible to the source and in such a way that the strategies best maintain or restore the watershed's hydrological and ecological functions. Examples include using swales instead of piping, promoting sheet flow to natural areas, and reducing the width of paved roadways. So let's look at a real-life case study that pursued option 1. Here's a 27-acre site with 95% impervious area in Portland, Oregon. If the 95th percentile rainfall event, 1.0 inches, occurred on the existing site with no control measures, 0.86 inches of runoff would be generated and require management. Given these site conditions, there is not enough pervious area to manage the entire runoff volume discharged by the 95th percentile rainfall event with bioretention alone. As a result, other practices were evaluated and selected. The practices integrated into the design included a vegetated roof, cisterns, and porous pavement. Based on the technical considerations of constructing and maintaining control measures at the site, it was assumed that approximately 30% of the available pervious area could be converted into bioretention cells. 20% of total rooftop area could be converted into vegetated roofs. 40% of paved area could be converted into paver blocks, and 50,000 gallons of total volume could be captured in cisterns for use on this urbanized site. Using this system of 4 different practices, all runoff for the 95th percentile rainfall event would be retained. A total of 1.3 acres of the site is pervious area or landscaped, of which 0.4 acres or 30% of the pervious area could be converted to bioretention cells that have a storage depth of 10 inches. Of the 8.8 acres of current rooftop area, 1.7 acres or 20% of the rooftop area could be retrofitted into vegetated roof areas. Of the 16.9 acres of paved area, 1.4 to 3.5 acres, or 8 to 20% of the paved area, depending on the soil type present, could implement paver block systems. 1 or more cisterns could be used to capture up to 50,000 gallons of runoff from rooftop areas. The high percentage of imperviousness of the site, about 95%, requires that all infiltration designs be based on resident soil type and design volumes, or with adequate subbases or amended soils. Now, OSHA classifies soils into 3 main groups: Type A, Type B, and Type C. Type A is the most stable, while Type C is the least stable soil. To determine the soil type on a construction site, there are several tests that can be used. Following a visual test, a plasticity test can determine if the soil is cohesive or granular. For cohesive soil, the thumb penetration and pocket penetrometer tests help determine the unconfined compressive strength. Determining the type of soil on a site will help to decide which methods of sloping, benching, or shoring are needed to prevent cave-ins and keep workers safe. Let's look at another project, a 21-acre site with 70% impervious area, this time in Atlanta, Georgia. If the 95th percentile rainfall event, 1.77 inches, occurred on the existing site with no control measures, 1.17 inches of runoff would be generated and require management. The runoff from the 95th percentile rainfall event could not be adequately retained solely with bioretention systems. Based on the technical considerations of constructing and maintaining control measures at the site, it was assumed that up to 15% of the pervious area could be converted into bioretention cells, and up to 40% of the paved area could be converted into a paver block system. If the rainwater management techniques used on the site included both bioretention and paver blocks as presented here, then all runoff from the 95th percentile rainfall event would be controlled. For the site in Atlanta, areas of 1.8 to 4.1 acres, depending on soil type, would be required to manage the runoff discharged from a 95th percentile rainfall event. Assuming that bioretention practices are only placed in areas that are currently pervious or landscaped, a total of 6.2 acres of pervious area is available for the placement of bioretention systems. The designed storage depth of media within the designated bioretention area was 10 inches. permeable pavement systems could be used to treat the remaining volume on the 10.8 acres of existing paved area. In applying the TR55 model Natural Resources Conservation Service method, the overall curve numbers for the site were 87 and 91 for Group B and C soils, respectively. TR55 was used to estimate 0.73 inches of runoff for soil Group B and 0.97 inches for soil Group C, which are smaller numbers than the 1.17 inches of runoff estimated by the direct determination method. As a result, the sizes of the on-site control measures designed using the TR55 model were smaller than those designed using the direct determination method. It is recommended that caution be exercised when using TR55 to model storms less than 0.5 inches per event. Now let's discuss Option 1, Path 2 for the rainwater management credit. This is rather straightforward in that the design team would follow all steps under Path 1, but instead substitute the 98th percentile for the 95th percentile. Path 3 is the final choice under Option 1. Path 3 is for zero lot line projects only at the 85th percentile. There are three main steps to achieve compliance under Path 3. First, confirm that project qualifies for the zero lot line path. The typical zero lot line project is an urban site for which the building footprint aligns with the site limits and the lead project boundary. If the project does not exactly align, but nearly aligns, provide justification for why the project qualifies for the zero lot line path. If it does not meet this condition, it is ineligible for this path. Calculate the average density of the area within a quarter mile or 400-meter radius of the project building. If the density, expressed in terms of floor area ratio, is less than 1.5, the project is ineligible for the zero lot line path. For the next step, determine the value for the 85th percentile of rainfall events. Follow all steps under Path 1, but substitute the 85th percentile for the 95th percentile. The final step is to design green infrastructure and low-impact development strategies to manage runoff on site. Follow the steps in Path 1. Green roofs and rainwater harvesting approaches are the most likely strategies to help zero lot line projects meet the credit requirements. Roofs can be either extensive or intensive systems. Maintenance will be needed to keep plants healthy and the structure in good condition. Artificial turf is not an acceptable strategy for vegetated roofs. In some cases, zero lot line projects can also use infiltration planters, porous pavement, and tree boxes. Here is a chart showing the required documentation needed to achieve the rainwater management credit. All projects must have rainfall data, rainfall events calculator or calculations for the chosen percentile, runoff volume calculations. Also, the design team needs plans and details depicting site conditions, strategies, direction of water flow, etc. The design team is also required to provide a narrative confirming measures qualify as green infrastructure or low-impact development. Calculations for volume of rainwater managed by low-impact development and green infrastructure need to be included, as well as an explanation for why 10 years of historic rainfall data may not be available for the project location. For multi-tenant complex projects only, there needs to be a summary of centralized approach and associated distributed techniques. For Option 1 Path 3 projects, the required documentation also includes a description of conditions that make the project zero lot line, as well as the floor area ratio. It's also important to note that the rainwater management credit can contribute up to 3 points for O&M projects, specifically existing buildings. The intent is identical to the new construction credit, which is to reduce runoff volume and improve water quality by replicating the natural hydrology and water balance of the site based on historical conditions and undeveloped ecosystems in the region. However, the requirements are different than for new construction. The requirements are that the design team must use low-impact development practices to capture and treat water from 25% of the impervious surfaces for the 95th percentile storm event. Establish and implement an annual inspection program of all rainwater management facilities to confirm continued performance. Performance requirements include documentation of annual inspections, including identification of areas of erosion, maintenance needs, and repairs. Perform necessary maintenance, repairs, or stabilization within 60 days of inspection. Low-impact development and green infrastructure measures must be in place by the end of the performance period to satisfy the credit requirements. Rainwater management is crucial for designers to implement for a building project. Rainwater management that utilizes green infrastructure brings nature into the city, which can improve both mental and physical health, increase property value, conserve energy, enhance wildlife habitat, and save money. We hope you've enjoyed our course, and we wish you good luck on your next LEED project.